Okay, so this is the example that we did last time, right? So we had this polynomial function there. It was a quadratic function. And then on the right-hand side, we had n squared, right? Okay. The question was f of n big O of g of n, right? Was it? So when we defined big O, we said that there's this in the back of our minds, we can keep this less than or equal relationship in place of big O, but in a qualified sense, in the asymptotic sense. So what do I, to be more precise, you have f of n being big O of g of n. We're saying that in some sense, that f of n, the guy that stands on the left-hand side, f of n, left, is less than or equal than the guy on the right-hand side, g of n. But in what sense exactly? Like last time we claimed, we actually showed that f of n was big O of g of n. But clearly you will say, f of n is not big O of g of n. It's not big O of g of n because if you, let me collapse this here. You don't need this. So if you plot these two functions here, here's g of n is the orange function here. G of n is clearly below f of n. Yet we claimed that in some sense, the orange function is bigger. How is it bigger? Well, you get to multiply g of n by a constant of your choosing. If you multiplied g of n by 1.5 or something, it will still be below f of n. If you multiplied it by 2, it would still be below f of n, right? Because f of n has 2n squareds and plus some change here. And that change will allow f of n to stay above g of n if g of n is multiplied by 2. So comparing functions 2n squared plus change with 2n squared. 2n squared plus change is still going to be above. But you get to pick the constant. So you can choose 2.0000001, or to make life simpler, simply choose c equal to 3, the constant. What is the c constant again from the definition? Here's the definition. So you should always keep the definition in mind. You can put it on like a sticky note or something and put it in your pocket, whatever. Just have it next to your homework assignments. Okay, so when you do choose a c to be equal to 3, then what happens is when you plot this function, okay, so now what we have is we have the same f of n, but now what happened to g of n as I stretched it by like 3 times? Well, what happened is that now I have an intersection point between the f of n, the blue f of n, and the orange g of n. This intersection point here, after this intersection point, the orange line will always stay above the blue line. Okay, they're both parabolas here. So what's the intersection point? Well, you have to solve the following, right? You want to know for which x's, or in this case, for which n's. So you want to solve when this is equal to 3n squared, right? Okay, now this is a quadratic equation. So you throw 3n squared over to the other side, you'll have minus n squared plus 16n plus 6. Well, when does that equal 0? Okay, so you solve this equation, it's a quadratic equation. You know how to solve this. So when you solve this, you'll get an answer. And the answer that you will get will be something, all right, this is about 16-ish. Okay, so this is, okay, so first of all, you don't care about the negative root. Okay, so you don't care, we care about positive n's. So you throw out that solution. So here's the solution that you care about. It's about 16.4-ish, 16.5-ish. Okay, that's the answer. So how do you wrap up your answer if you saw this question on a quiz? What are your witnesses? So yeah, to show that one function f of n is big O of g of n, you have to exhibit the pair of constants, the so-called witnesses, the c and k. You have to write down c and k. Okay, so let me just put these both at on the same like line. First of all, I want to get rid of these warnings here. Here's the okay. Here's the same picture that we had above. So again, the orange line was below the blue line, but when you got to stretch the orange line, it now turned into this green line. 3 times gn is this guy, and now you have an intersection point. And the intersection point was going to be at 16 or whatever it was, about 16.5-ish. So you say that whenever the 17 then is my k, as long as as long as n is greater than 17, this 17 is the intersection point here. As long as n is greater than 17, the green guy will stay above the blue guy. What's the green guy? The green guy is the multiple of g of n, some constant multiple of g of n. Important that it's constant. And the blue line is just the original function f, which you needed to estimate. Okay, bound from above. That's what I mean by estimate. Well, you need an upper bound on that function. That's what big O is all about. It's all about the asymptotic upper bounds, right? Whether it's worst case, best case, whatever runtime it is of a function, of any function. Okay, so people remember this. So last time we filled out a little bit of a table. So but you can just as well draw it in your favorite software package, whatever it is you use to draw these things. Okay, so you can do it in MATLAB or like here in Python, whatever makes you happy. So the thing is that you could have picked a completely different pair of witnesses. Okay, so there was so we stretched this g function 3 times. Okay, so and when we stretched it, it intersected the blue line. But it didn't have to stretch it. You can stretch it by a different amount. So this time, you're going to multiply g of n 5 times. And when you do multiply g of n 5 times, the intersection point becomes lower. So now it's about 5.5-ish. If you solve this same equation here, instead of 3n, you solve a different equation for an intersection point. You'll get a different answer. You'll get this answer. And this answer is about 5.7-ish. 5.7-ish. So you say then, as long as your n is 6 or bigger, again, we care about integer n's. As long as your n is 6 or bigger, for this c, it is true that constant multiple times or the orange function, so constant times g of n, will be above, always, forever, for all time, will be above the blue line. All right, so this is, in a nutshell, this is what big O is all about. Now, let's stop here for a second. Does that make sense to people? But let's go through a bunch of examples. Is it true? Now, we did this one last time, so let's do it real quick. Is it true that 2n squared is big O of n cubed? Well, what am I trying to do? I'd like to make it less than or equal than some multiple times n cubed for all n that are greater than or equal some k. So these c and k are the witnesses. Always keeping them in mind. Okay. So what c and what pair of witnesses? Just ad hoc. What pair of witnesses works? You can always, by the way, in big O questions, okay, in real analysis, you'll probably cover small o. There it wouldn't work. But for these questions, you can always fix one of the constants and the other depends on it. So c, you can fix c, and k, you can select k based on c, as we did in the example. Essentially, when we fixed, for example, the fn and gn example a few minutes ago, when we fixed c to be 5, k changed depending on what the value of c was. So k depended on c.
Let's make C2.
Okay, let's make C2. Okay, so we make C2, then what happens? For which n's does that work?
For all n's.
So let's see.
I guess we say greater than or equal to 0.
Yeah, exactly. So let's start with k equals 1. It's true. So 2 n cubed. Okay, so n cubed. So because k is 1, so 1 cubed, this should be cubed here. It is true that this, okay, is certainly true that this is going on for any, right? So we've just found for any k, right? Well, it's certain that because we are, well, actually, can I go back for a second? You suggested 0, which was a good suggestion. Just to nitpick, if k is between, like, because we're restricting ourselves to integers, that's fine. So nobody's going to nitpick about this. But according to the book's definition, which also allows for reals, that actually wouldn't be a correct answer because if
Yeah, that makes sense. It'll be smaller if it's between 0 and 1.
yes.
Okay, so we should consider non-integer cases as well.
No, yeah, you don't have to, like in the examples, like on the quiz examples, ends will normally be integers.
Okay.
You just fix something like k, it works, right?
Yeah, I'll just make sure to state if it's an integer or not, if I'm assuming.
Yeah, good point, please do, yeah. Okay, all right, so how about this one? Is it true that n cubed is big O of 2n squared? N cubed is less than or equal some constant multiple times 2n squared. 2n squared is my function g, so this is my g of n, and this is my f of n. Of the definition, that's the roles played by f's and f and g, respectively, here for this example. Okay. Can I make, that is, can I stuff the stuff? So what does it mean to, what does this mean? This means that you can stuff the n cubed function underneath some constant multiple of this function for large enough n forever. That's what big O definition means. Stuffing it underneath for large enough n. Okay, so you might be thinking, oh, okay. Okay, if I selected a large, super big, like C, like 10 to the 80 or something like that. Okay, so then maybe I can stuff it underneath. So what do people think? Can I select such a pair of constants, C and K, for which this definition will work? Okay, so again, every time the definition, you're keeping it in your pocket. If you forget something, you just take it out of your pocket, looking at the definition. After a while, it's in your mind. You don't have to keep a physical external.
It's not possible to select a C large enough.
Sorry, one more time. It's possible?
I do not. I know. I don't think it's possible to select large enough.
Okay, so anyone else?
I mean, C is constant, so I don't think so. Like the only other thing, I guess, maybe making it n, but then it's not constant. So.
Okay. Yes, you have the right intuition, right? Anybody else? But we need to prove this. We need to show it. That's so we have now we have the intuition. Now let's see if we can concretely write this down some convincingly to a person who's not convinced perhaps by this, by your intuition. So let's see what we can do. Okay. So the answer is that no, it is not. N cubed is not big O of 2n squared. Proof. Our proof is by contradiction. What's proof by contradiction? By the way, you will always write this down in your submissions. Is by contradiction. Just to alert the reader that you're about to write something down. It's a paragraph of your argument, let's say. Okay, no proofs here will be longer than 2 or 3 paragraphs, right? So this one is like a few liner, few parry. Proof is by contradiction. Help me out. What's that by contradiction? What does that mean?
You just try to prove the opposite of what you were originally trying to figure out, I guess.
Okay. Suppose.
So like,
yes.
Oh, no, never mind.
Yeah, suppose by way of contradiction that n cubed is big O of 2n squared. Okay. Now this is called in scholastic times. This argument was called reductio ad absurdum in Latin. And this is sorry for my horrible Latin pronunciation, but that's what it was. Reducing your argument to absurdity. You assume something, and then you have an unassailable chain of logical deductions, and at the end of this chain of deductions, you arrive at an absurdity, and therefore your original assumption must have been wrong. That's reductio ad absurdum proof. Or as we call it today, proof by contradiction. You assume this and see where we get to. So suppose by way of contradiction that this is in fact the case. Then what happens? Then that means that I apparently can find constant. Then say some C and K work as witnesses, right? So you can fit the definition. Then for some K and C, we have we have that n cubed is less than or equal c times cn squared for all, okay, for all. Now, what can I conclude? What can I deduce rather from this? Won't be a conclusion. For all n that are greater than or equal that k. So I'm assuming by way of contradiction that n cubed is big O of 2n squared. Therefore, if that's the case, if somebody gave me those two constants, c and k, well, I don't know what they are, but because one is big O of the other, those c and k exist. So, okay, let's consider those c and k here shown in red, those c and k. So this must be the case, right? Well, what does that say? Okay, then, okay, so that was, well, I guess if you want in terms of bullet points, then, which is the same, or let's write it down, which is the same as, this is kind of, which is the same, which is to say that, can I divide both sides by n squared? I mean, n squared is a positive number, strictly positive number. So if I divide two sides of inequality by n squared, inequality doesn't flip. So this is the same as n being less than or equal this c times I guess let's put it that way, 2n squared, right? What did I just write? C times 2, right? I divided both sides by n squared, right? So what is it saying now? Now it should be more or less clear what the absurdity is. The absurdity says that for all n that are greater than some number k, no matter how large, okay, it will be the case that this increasing n can be bounded above by a constant, which is exactly the intuition that you had like a few minutes ago, right? Am I correct? Right? So this is not possible. Why? Okay, but if you pick n, so let's call this star, this inequality, but pick n greater than or equal, well, technically it should be greater than or equal the k you gave me and c times 2, the max of the two. But let me just be a little loose here and say that c times 2, actually pick n equal c times 2 plus 1, just by 1 bigger. This n violates this, okay? Pick n, okay, so this n makes inequality, the star inequality, this guy, inequality, equality false, right? Okay, so what's the absurdity here? What's the absurdity to which we reduced our argument? We're saying that forever increasing n, unbounded n, is always smaller than some predetermined constant, no matter how big that constant is. Well, twice that constant c, but whatever, it's still a constant. Does that make sense? So this is the whole argument. This is actually a proof by contradiction. Okay, it could be revised, written out neatly, whatever in your favorite software, but that's the proof. Any questions about this? So apparently, n cubed cannot be stuffed underneath some constant multiple times n squared, no matter how big that constant is. That's what makes, by the way, that's what makes n cubed a higher order polynomial than n squared. It's asymptotically larger. That's what you knew all along from like calculus examples and so on and so forth. All right, does that make sense? Does that make sense? Okay, so here you have an answer for the first one. You have these. Okay, we just did this one, this puzzling question, for which we had an intuition, and that was the proof up above.
And we're going to need to write something similar on tests and quizzes.
Yes, you might need to. Okay, so the argument is not going to be much longer than what we just gave. So please make sure you understand these things. right? Okay, so you'll have questions like, so how about, can I ask you now the following sequence of questions then? Is n, okay, so which one is true? N is big O of n squared. That's true,
Yes.
right? Okay, so what are the C and K if somebody asked you? I'm not asking, but.
You
So-
can say says 1.
Yeah, just one and one work. And in the following examples, you see that this is also big O of n cubed, right?
Yes.
That n is big O of n to the 17th. And that n is big O of n to the 17.0001, right? Or any other number. I mean, just a random number. It doesn't have to be, right? Does this make, so why? Because in our sense, we can say that the n is smaller. This is all less than or equal everywhere in our asymptotic sense. So in this case, it's just less than or equal as long as n is bigger than 1. So so our C constant is 1. In general, what will happen is that when it comes to polynomials, and I'll prove this if we have time, but more strictly, but here, let's say you have two polynomials. So polynomial, let me just call them f without p of x and all of that. So you have f, yeah, okay. So f of x, let's call it x, fine. F of x polynomial on the one hand, so you have this x to the nth power, right? And then you have like, these are a's are some constants. Like this is just a general way of writing down a polynomial. So you have this polynomial, okay? Okay, so you have this polynomial on the one hand. On the other hand, let's say you have this other polynomial. So let me move this a little bit. Okay, so this is on the one hand. On the other hand, you have g of x, another polynomial. Okay, so let me actually mark this fn. Can I call this fn of x? Do you mind? It's just a polynomial of degree n. And I'm going to mark this a polynomial of degree m, let's say. That's just a marker so that I know. So here you have like this guy has its own constants, like x to the m and so on. E1 x to the m minus 1 and so on, right? So you have x and plus even. Okay, so you have two polynomials. Now, when is one big O of the other? So
when m is less than m.
Yes, exactly. This is happening whenever, in fact, n can be equal to m. Whenever n is greater than or equal m. And this is an if and only if statement. The converse of this is not true.
You have said that n is bigger than m.
Oh, I'm sorry. Yes, I have lied. That's why. That's that way. Thank you. Right? Thank you. Does that make sense? Okay, so if n is greater than m, then f of n is not big O of g of m. Makes sense, right, to people? Everything? Okay, great. So, all right, so we don't have time for a break. Let's continue. This is what we, okay, so now let's do a couple of, this is straight from the book. This, you can help me out. So now, obviously on the quest, you won't be able to plot the functions that I just showed you. So you have to sort of do this algebraic manipulation to convince people that your C and K work, okay? So here's my f of x. Here's an easy, a straightforward way of picking out the C and K. Let me paste again my definition, just to have it on the side. So, but by the way, I want to make sure that to do this the way the book wrote it out, so that the book's explanation is clear. Here's what the book does. It writes down this f of x. And of course, it wants to make this f of x smaller than x, some multiple times x squared. So here's what it does. It says, as long as your x is greater than or equal 1, it writes it down. So you clearly x squared is going to be less than x squared, right? So this is less than or equal x squared. Plus, clearly 2x is going to be less than or equal to 2x squared, right? So this is 2x squared. Clearly, then 1 is going to be less than or equal than x squared, right? So he writes down x squared here. Why does he do that? Because now he can add up these x squareds, and I get 4x squared on the right-hand side. So what I got in this chain of inequalities here, that whatever's on the left-hand side is sure to be squared, because as long as x is greater than or equal than 1, then this works, because I've substituted each of these terms by something that's bigger. So now it's clear. This is going to be my k. So this is going to be my k, and this is going to be my c. So witnesses, c equals 4 and k equals 1 work. That's the conclusion. Now, did I have to select? So notice that in this example, in this particular example, we fixed k and then we found c based on k. So again, c depends on k. These are constants that depend on one another. If you will see big O, small o in the future, won't be the case there. But here in the big O, these constants depend on one another. When you pick one, the other can't be completely freely chosen. Now, how about, now, can smaller c's work? So I claim that even c equals 2 will work, because I can dominate this polynomial by 2x squareds, 2. In fact, by 1.1 x squareds, I can do 2. But let's see. How about now, let's try to like another solution. So this is another solution. I want to say that this is going to end up being smaller than like 2x squared. What should x be then? I want to make this smaller than actually 2x squared. No, let's make it simple. Let's make, well, still different c. Let's make it 3. Would that be simpler? Well, let's stick with 2. Let's make it just more to worry about a little bit, just for practice. When can I make it this? When can I make this guy smaller than 2x squared? How about when? So try x. So k equals 1. So when x is greater than or equal 1 is what we're concerned about. So plug in x equals 1. Does this inequality hold?
No.
No, it doesn't hold, because on the left-hand side, I have 4, right? 1 plus 2 plus 1. And on the right-hand side, I have 2. 2 times 1 squared.
Couldn't you just set them equal to each other and then solve?
Yeah, solve it. Yes, you can. But let's go with trial and error. So let's just go, yes, clearly, yes. But notice that if we actually solved it directly, what we're solving is a quadratic equation. So this, let's make it in gray. So you're solving essentially x squared. Take this to the other side, minus 2x minus 1 equals 0. Okay, this may be easy to solve, okay? So you'll find that x is 2 plus minus 4 minus 4, right? Oh, okay, so is that right? Right? So that's the answer. You have 2 plus square root of 8 over 2. That's the answer. You need one of them. But why bother through this when you can, by trial and error, you have this freedom, this flexibility of it. Do you really want to be solving the quadratic equations? No. So what's so K1 didn't work. So how about K2? K equals 2, not K2. I mean K equals 2. This K equals try K equals 2. So what do I have in this? So it's a little trial and error. So let's just do it. So then what we have is 2 squared plus 2 times 2 plus 1. Is it less than or equal 2 times 2 squared? I have 8 here. And I have what? There.
9.
Yeah, so it doesn't work. So it doesn't work. But as soon as you go over this 2, phi k equals 3. So now I'm considering all these x's are greater than or equal 3. Then what I have is that 3 squared plus 2 times 3 plus 1, is it less than or equal than 2 times 3 squared? Okay, so you have 9 and 6 and 1, that's 16. So we have 16 here, and this on the right-hand side, I have 18. So this time around, this works. This k equals 3 works. So witnesses C equals 2. Okay, so this was one pair of witnesses here. C equals 2 and k equals 3. Okay, also work. Make sense? Because we just fit the definition to this particular example. All right, are people beginning to feel comfortable with this? So you kind of have to read a few times. It's not like just read once and so on. Okay, so this is the example to keep in mind. So what did we do? Let's pick out our first pair of witnesses here. Okay, so our first pair of witnesses. Okay, so this example has this pair of witnesses here. How so? Well, here was the original x squared. Is this guy. X squared. Well, it was below my f. Was below my f. But as soon as I multiplied by a constant 4, it became stretched in such a way that the tail of f of x was stuffed underneath this 4 times g of x. So once I managed to stuff the tail of the original function underneath my new function, that normally that g of n or g of x is a simpler looking function than f of x. Then we're done. Where is the intersection? Well, it's at k equals 1. Well, as long as, exactly, k is 1. This is k. As long as k, for every n, or in this case, x is the variable here. These are all these x's that are greater than or equal 1. All these guys, like there, forever. All right, does that make sense to people? Okay, now let's do more examples.
I have a question
Yes.
about on the previous one. It's just a coincidence that like the C's and the K's look like they're related by 2, right? Like that's just
Yes, it's
like there's no
supposed-
relation. Okay.
Yeah, if you change like one constant here somewhere, then C's and K's will slightly change. They may not change. It depends. You have to. Yes, the fact that they're. Oh, hold on. What's the relation that you noticed?
Well, C. So the first one we got was C is 4. Then in the second one we got C is 2, but then K went up by 2 as well to 3 from 1, right?
Oh, so you've increased C by 2 and that K went down by 2. Yeah, that's a coincidence.
Okay.
Right. So yeah, it's okay. So that's an interesting thing to notice, but that's a coincidence. I mean, it doesn't have to go down by 2.
Okay. Thanks.
Right. So that's interesting. Okay. So, all right. So fine, real quick, since this is here now, this one you'll probably do quickly. What is this true? Big O of x cubed. Is or is not?
Is
What's the constant?
7.
7 times x cubed will work as long as x's are greater than or equal 1. So answer. C is 7, for example, K is 1. And you're done with this quiz question. 2 seconds. Throw in a couple of words, make sure, it's just neatly written, and that's it. So now all of a sudden it just became quick. All right. Why is n squared not big O of n? We did this. We're kind of repeating this, but why is it not? Now let's not write it out, but let's give an argument like a 2, 3 sentence argument.
You divide it by n, and then n can't be less than 1.
Okay, yes, if it were. So answer is no. If it were, then n would be less than or equal a constant, which then that would be then n, which cannot happen, no matter how large c is, because n grows without bound. Does that make sense? And that's exactly the reason. So that's, again, it's a proof by contradiction, but this time, now that we've done that and written it out, this one was quicker, right? Make sense? Okay, let's go on. Okay, so let's not, okay. Is it true or false? We're not going to write it out because we did something very similar. We want to do something like different examples now. Is this true or false, this guy?
False.
Yeah, it's false, right? For what reason? Same reason, right? As you just gave here. Right? Make sense to everyone? Are we on the same page? If not, please ask me. And okay. Okay, how about the polynomials? We just talked about polynomials. Right? Okay. So here's what you see in your textbook. So you're given this polynomial of degree n, right? So you have this polynomial here. Okay. So these are, all of these are coefficients. So a very loose way of putting this, we'll in a second. So the point is that this is big O of this guy, the largest power, big O of x to the n. Can somebody help me out? What is this argument all about? Do you see? So what is it? So let's go through this proof real quick. Why is it the case that f of n can be made less than or equal than x of n? How can it be made less than or equal than x to the power of n times some constant c? How can it be made? All right. So ignore these modulus signs. Assume that they are positive, and then you can worry about the details later if you'd like. So just for simplicity, and then you'll extend your argument later. Just for simplicity, just assume that all these a's are positive. So you have, just if you want to write something down, always if it secures in your mind as you're going through these proofs, write a concrete example down. Like, I don't know, 7x cubed plus 2x squared plus 12x. Okay, now I'm it's a bit of overreach, that big numbers. It could have been much smaller, but okay, so you wrote down. So some of these coefficients here could be 0, but you wrote this down. And you want to prove that this is going to be smaller than c times x cubed. Now, each of these guys, and we just proved that, each of these guys, this one, and this one, these three terms, okay? These guys, each one, the first one is certainly less than, as long as x is greater than 1 or bigger. This guy is smaller than that. This guy is smaller than that. And this guy is smaller than x cubed. Okay, so how many x cubes do I have? I have 7x cubed here, plus this many x cubes. So what am I doing? I'm adding up the coefficients, sum of coefficients, and it's going to be smaller always. Does that make sense? Do people see this, what we're doing here? So when you add those up, you're essentially adding up 7 plus 2 plus 12 plus 1. So what we're claiming is that as long as x is greater than or equal 1, and that's my k, as long as x is greater than or equal than 1, then your polynomial, and instead of this, I'm going to write down my 7x cubed plus 2x squared plus 12x plus 1, just in general, it's less than or equal than 7. Well, let me write down just in one step here. It should be, if it's not clear, just stop me. Plus 2 plus 12 plus 1 x cubed. Does this make sense? Does this make sense given this? Right? So now that sum is just the sum of all these guys. Okay, that's what it's saying. So this is a proof that fn of x is going to be always at most asymptotically as the highest power of x of n. Based on this theorem, it is based on this theorem that we say that vague phrase, oh, constants don't matter and we can drop lower order terms. When we say that based on this theorem that we have just proven. Does that make sense? Because we just, this is big O of x to the n. So we just dropped this constant, or any other constant for that matter. We dropped that constant and all these lower order terms. And we just say that we're extracting the essence as far as big O definition is concerned. We're extracting the essence asymptotic if you can say it, in asymptotical essence of this polynomial function. If you can say that, you can say that. What's most important about this function is its highest order term, and all these constants don't matter, and lower order terms can be dropped. That's what it is. Okay, so that's that. Okay, let's do this example. I want to know how much time do we have. All right, let's do this one because we came across it. So I don't want to skip it. Now it's on the screen. So let's do these guys. 1, 2, plus 3, plus blah, 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 plus n. What's the big O estimate of this sum? The sum of the first n integers. Any suggestions? So which one is correct? Is big O of n, is big O n to the fourth, is, so several of these are correct. Big O of n 2168 is big O of n squared. So which one of the, so this is, let's call it A, B, C, D. Did people sign in? Yeah, I think we just closed the sign in. Okay, so which one is correct? So let's call this like S of n for sum of the first integers if you want. You can call it f of n. Let's call it f of n if that confuses you. That's my function, f of n. It depends on n. N is an integer, and it's the sum of the first integers.
Be D.
D and, yeah, D.
Okay, let's start with a D. Okay, so the D is correct, but it's not the only correct choice. Okay, so why is it? Why is it? Later you'll prove, so later, just this is heads up, this is complete aside, you will prove that this sum is going to be, you've seen this before, it's an arithmetic progression if you remember from high school. If you don't remember, so what, but that's, the sum is going to be that. You'll prove this by induction for practice, but you clearly don't need an induction to prove this. Again, this is aside. How would you estimate, so okay, so let's forget we know it. How would we estimate this? So you have 1 plus 2 plus 3 plus blah, 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 plus n minus 1 plus n, right? This stuff is less than or equal n plus blah, 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 plus n plus n. So this n is that. As long as n is, this is true for any n greater than 1. This n is bigger than 1. This n is bigger than 2. That's instead of this 2, we got this n. Okay, this 2. The third n, this guy, this n here that sits there, that was greater than 3, and so on. This n is less than or equal n minus 1. N minus 1 is less than or equal n, and this is less than or equal than n. So because each term is a larger term here on the right-hand side, and how many of these guys do I have? 1 for each term. So I have n of these guys. Okay, so apparently this then equals n times n. Otherwise known as n squared. So n squared is always larger than that, than the left-hand side. Do people see this? People agree with me or people disagree with me? If you it's always good to disagree and let everyone know. But I think it's hard to disagree on this one. So that's big O of n squared. Now it's a little bit, takes a little bit more to work that n squared is big, that n squared is big O of this f of n, right? But it's, so in this example, this guy, so f of n is big O of n squared, and the converse is also true, unlike a few other examples we said. N squared is big O of f of n. It works both ways. In those other examples, so both of these are true. In this example, for example, before, that would not be the case. So 7n squared is big O of n cubed, but n cubed is not big O of 7n squared, right? In this example, f of n is big O of n, is unlike that one, in that f of n is big O of n squared, and also n squared is big O of f of n. Okay, now, it's big O of n squared. Is it also big O of n cubed?
Yes.
Yes, it's also big O of n squared, because if I can bound this f of n above by some constant multiple of n squared, I can also bound it from above by some constant multiple of n cubed, because the n squared itself I could bound with some constant multiple of n cubed. So I can definitely bound this one, right? This kind of transitivity at work. Does that make sense, what I just said, or should we write it in detail more? So it is big O of n cubed. This f of n is also big O of n to the fourth, right? In fact, of any other higher power of n. What we'll have to work with is that f of n, so this is true, so this is true, this is true, and this is true, and this is not true. It's not big O of n, f of n, right? So that may be homework assignment. I don't know. Okay. All right. So what else do we need to say here? Now, let's do one example with logs or somewhere. Do we have? No, we need some scratch paper. Okay. So these are. Okay. So let's ignore. Okay. So now I'd like to show you. Okay. Let me ask you about this one. You have on the one hand log of x, and on the other hand, okay, what's x to the fourth? This is my f of n. And on the other hand, you have g of n.
F of x. F of x.
F of x, okay. F of x, let's call it, fine. And on the other hand, you have, let's get more dramatic with colors, I guess. G of x, you have log of x. Question 1. Is f of x big O of g of x? And is g of x big O of f of x? That's the question. Okay, let's start from here. Now, which one is true? Maybe neither, maybe both, maybe only one of them. So again, big O, I'm thinking f of x is big O of g of x if I can stuff f of x underneath g of x. So if I can make f of x smaller.
In this case, can we use the identity from logarithms?
Of course, you can use anything that you know. Of course you can.
I can say that's 4 times log x has to be less than log c times.
Yes.
C times log of x, and we just have to find the c.
Yeah. So when is this? When is? By the way, the base of this logarithm, let's say it's 2. So any base greater than 1 will work. Well, what happens if the base of the logarithm is less than 1? When you have a decreasing logarithm, we were not concerned. So you have logs your log. Okay, so for any base, this base here, let's say it's 2. The base is positive, then you have some function like this, right? It's a base. It always calls it 1 here, but no matter what the base is. But anyway, so because of this, despite the fact that you have the power inside the argument, now it would be a completely different story if you had this to the 4th power, and it's not what we're talking about. But you have the 4th power inside the argument itself of log. So that tells you that's the feature. That's what log is. That's the essence of a log. So log of something to some power is that power times the log, right? So that's this is true. So this is less than or equal. So 4 times log of x, and rewriting this is kind of silly to write, but this is my c. So 4 is my c. So witnesses. Okay, so why did I talk about the base here? Well, this holds for any x greater than or equal 1, not the base, but rather this argument here, no matter what the base is of the logarithm, as long as the base itself is bigger than 1. Okay. So witnesses are like, so c equals 4 and k equals 1. Okay. This definition fits perfectly as long as c is 4 and k equals 1. How about the other way? How about this guy now? Is this guy big O of that guy? So I'm flipping the
actually, the way we wrote it, we answered first that g of x is big O of f of x.
We answered that f, this is f of x.
Because we can say that log of x, I'm just saying that the way we wrote it, we can say that log of x is less or equal than 4 times log of x.
Yes.
So we kind of have answered already.
Yes, that is true in that sense. Yes, this is also true, because because log of x is also less than or equal. Yeah. So what did you answer? It's because it's less than or equal 4 times log of x, which in turn equals log of x to the 4th. You just simply, what's the constant now? Simply pick out the constant to be 1. So that suffices. Right, so c equals 1, and k equals, well, 1 again. Work for the other way. Work for this. Works here. Make sense to everyone? Right? Okay, so how about if I had something like the example I'm going to show you now? I'll switch the screen with the few minutes that we have left. So how about if I had log of x to the 4th? I think the example I have here, I think pretty sure that was it, compared to log of x. Okay, now I have this extra wrinkle here. Let me switch the screen. So what do you guys see right now on my screen? Okay, so do you guys see my screen right now? This is a log example. Yes. Should be a notebook there. Okay, so what's happening with this example? So I want to show, is this big O of this guy? Just simply log of x. So which c and k work? Okay, I want to show that this will hold. Well, let's plot this guy. So if you plot this guy, this is already, we run all the cells. If you just simply plot these guys, the blue line, the left-hand side, my f of n. So f of n, again, to the left side, g of n to the right side. G of n should be the simple function. F of n is the function that you're trying to estimate. That's the guy to the left. Just keep that in mind. So this is now log of this, the not simple function, is above. So what we'd like to do is to make somehow the blue function stuffed underneath the orange function. Now, if I went ahead and multiplied that log of x, let's say by, this is already run again. So if I multiplied this by 3, okay, so the orange guy from above, this log of x is now multiplied by 3, and it goes up a little, but it still doesn't cross the log of the blue function, still doesn't cross it. It's still underneath the blue function. So this constant c equaling 3 wouldn't work in this case. But if you take the constant 5, so stretch it even more, then it crosses the blue line at some point, which point is easy to find out, let's say in Wolfram alpha, or just simply solving it. And so you find this, so after this point, you will have the orange line staying above the blue line, right? So, but again, on the quiz, you won't have an opportunity to write this, to draw these graphs, right? So you don't have access to stuff. So this is how you write it down. So you need to, this algebra magic kind of exhibition here. So you have log of this. This is my f here. You want to make it small. This is the end result. Some constant multiple here turns out to be 7. Okay. G of x is log of x. So I want to get from the first to the last somehow. And here's the chain of algebraic deductions. Okay. Do you guys agree that as long as, actually this one says x greater than or equal to, and that's what we need, but even if even for smaller x's, like if x is greater than or equal than 1, as long as x is just greater than or equal to 1, do you agree with the first inequality here? We've substituted 5 with 5x to the 4th. Well, x to the 4th is always bigger. So the argument here of a log in this second expression, x to the 4th plus 5, the argument is bigger. And log is a monotonically increasing function. So you give it a bigger argument, it will return to you a bigger value. So this is an inequality because log is actually increasing function. It would work if it was just simply non-decreasing, but it's an increasing function. So inside the argument, you have 6 of that x to the 4th. But 6th log of a times b is log of a plus log of b. So that's log of 6 plus log of x to the 4th. Now log of 6, well, log of 8 is 3. So log of 6 is something smaller than 3. So clearly log of 6, instead of log of 6, I can write down a 3 here and say that log of 6 is smaller than 3, definitely, just to have a nice whole number there. Didn't have to. But, instead of log of x to the 4th, well, that's 4 times log of x. Now 3 is definitely smaller than log of x, right? As long as x is greater, x, 3 is definitely smaller than 3 times log of x, right? As long as x is greater than 2, right? Right. So this is 3 log of x plus 4 log of x, a total of 7 log of x. So now on the right-hand side, I finally have some constant multiple times log of x. Okay. Somebody's asking why log of 6 is 3. It's not. It's at least 3. This one says it's less than or equal. It says less. Log of 6 is at most 3. So I can, instead of log of x, I can substitute something bigger. 3 is bigger than log of 6. Log of 8 is 3. And log of 6 is smaller than 3. Does that make sense? So on the right-hand side, I'm bounding it by bigger quantities. The right-hand side, I have bigger quantities. Make sense? I may have missed some of the chat.
Professor.
Because by accident, I looked at the chat. Yeah.
Professor.
Yes.
Where we have that the log of 6 x to the 4th is less than or equal. Yeah. Can we just put equal to that and then put
here? Yes.
Equality?
Here. Yes. Yes. This actually, let me just substitute that with equality right now. So you could have this is true. Where was this? X to the 4th. This is an equality. Okay. So that's an equality. Yes, you can substitute this as this. You can make this an equality. Right? Does that make sense? That is an equality. Okay. So the last thing I want to show you, this should make sense. The last thing I want to show you is that you have here a summary of all the examples that we just did. So let me open this up. So it's posted there. This is Big O summary. This is essentially, it's intended as a summary of today's lecture, plus a bunch of examples that you should do. So this, we started by reviewing the definition of Big O. Here you have the definition of Big O. Then we ran these examples. These are the examples that we ran earlier. This was the first example. Here are a couple of exercises here. So as you go through this, much of this already makes sense to you. Others you have to work through. You have a bunch of exercises. These exercises here, you have solutions to those exercises at the very end. So you see, like when you get all the way to the end, well, you have more exercises in section 2, and then you have selected hints or solutions to those exercises.